Okay, I'm still figuring this out. I couldn't pause it. I had to get interrupted. But our third bond, and by far my favorite bond, is the weakest. It's kind of like the universal Velcro of the biochemistry world, and it's what's known as a hydrogen bond. So, the good old hydrogen bond. And a hydrogen bond is not really so much a bond as it is an interaction, but let's not quibble with the terminology. A hydrogen bond occurs when we got a molecule that has an asymmetric distribution of electrons. Here's what I mean. So we're going to draw a molecule of water and appropriately draw it in blue. Water, that is H2O. Can you read that? Blue is not showing up so well. We'll stick with black. Water. H2O. All right. Water has two hydrogens and an oxygen. And we draw it like this. We've got oxygen. And then in the chemistry parlance or abbreviations, the line is the covalent bond. So that's water right there. Now, oxygen, it turns out, is an electron hog. It tends to keep the electrons right next to itself. It doesn't let them stray too far out very often. And so the electrons tend to be right around here, and once in a while they go out. But mostly they're going to hang right here. Now, just as a chemistry term, not that you need to worry about this as a vocabulary word, but this is referred to as being electronegative. Oxygen is electronegative. Let's see, fluorine maybe. A couple of different atoms are, but not all atoms are. Most atoms are not electronegative. Most atoms are good about spreading the electrons out. Now, what this means then is that in water, because the electrons tend to hang around oxygen, oxygen has a slight negative charge, and hydrogen has a slight positive charge. And what that means then is in a single drop of water, not much happens, or a single molecule. But if you add more molecules of water, watch what happens. We're going to make a charge network in that we're going to have an oxygen from this water molecule with the negative charge interacting with the positive charge of the hydrogen. And that interaction is what we call a hydrogen bond. So a hydrogen bond forms whenever we have an oxygen pulling the electrons away and then a hydrogen that ends up having a slight charge. And you can see now we can make a mesh network of water molecules as we start drawing lots and lots of hydrogen bonds. You can fill the whole board up, pardon me while I go ahead and fill the board up with hydrogen bonded water. What this means is water actually is quite sticky. Water behaves in some strange ways because we live in such an aqueous world, or with water. We don't really realize exactly how strange water is, but pretty much nothing else acts like water. Water exhibits capillary action. It gets pulled up a straw of a really narrow tube. Because the hydrogen bonding is very sticky, water has some fairly weird things that happen. When it freezes, water is less dense, frozen, than when it's in the liquid state. And that's partly because of the hydrogen bonds in the liquid state. One thing that happens is that ice floats, which is really good if you're a fish in a pond somewhere, up in northern Wisconsin where it gets really cold, and it starts to freeze. Rather than freezing from the bottom up, which is what would happen with a lake of liquid whatever, it freezes, but the ice is always staying on top. and so the fish don't get squished. Isn't that nice for the fish? Yes. So, just as an example, alcohol doesn't form a crystal structure when it thaws. And it doesn't form a puddle. It actually is like honey, almost like molten glass. So water has very weird characteristics because of the hydrogen bonds. All right, so these are 3 bonds, and we'll be using these different bonds to discuss molecules. We've got covalent bonds, which are an equal sharing of electrons. We've got ionic bonds, which are an unequal sharing of electrons. And then we have hydrogen bonds, which are essentially an electrostatic attraction between one atom that accumulates a lot of electrons, and then the other side of it doesn't have electrons. It's what's called a polar covalent bond, and that can form this interaction. All right, so let's see. A little bit more chemistry, and then we're going to call it quits for the day, because that's all I can do. All right. Another term that we'll find important is something called pH. Now, we could get all chemistry scientific on us, but nah, I ain't gonna. Let's face it, that's not what this is about. The idea of pH is a measure of how acidic something is or how basic something is. And it's based, as I say, is centered around water. And so we've got neutral in the middle. And this is essentially what water is going to be. Now, here's the way this thing works. And this is, I'm not going to get overly involved in it, but as I said, I've said it and you heard it, but you don't have to worry about trying to define it this way. It is a measure of the hydrogen ion concentration, and it's relative to water. So water, which is HOH, water will spontaneously break apart, but not much of it does. A very, very small fraction of it in a liter of water will be split apart. And it will generate 2 ions, a hydrogen ion and what's known as an OH group, or a hydroxyl group with a negative charge. So it is a teeny fraction. It is 1 times 10 to the minus 7 moles. That means it is a 0.00000001 moles of hydrogen. Not that you care, whatever. Rather than saying 1 times 10 to the minus 7, we take something that's called a P function, which is the inverse log. And I know you're saying, wait, I was told there wasn't going to be advanced math. Don't worry about it. It's like this. The logarithm, like 1 times 10 to the minus 10, we're going to take that exponent, drop the sign or reverse the sign, and use that. So 1 times 10 to the minus 7 moles of hydrogen in water. We take the P function, we call that a pH of 7. So, pH, neutral pH is 7. And this is the amount of hydrogen ion that is present. Now remember this, because we'll be talking about this later. The lower the number is, the more hydrogen ions there are, because this is the inverse log. So 0.000001 gram versus 0.1 gram. All right, that's what we're talking about. So things that are acidic have a pH of around 1. Now, things that are basic, and this is somewhat arbitrary just to make it so it's in use at 7, but things that are basic have a pH of around 14. All right, so this is the pH scale. It goes from 1 acidic to 14 basic. It's a relative scale. All right, just as an example, around pH 7, we got things like blood, sweat, tears, lots of body fluids. It's not a good name for a band, too. Yeah, see, back in the 60s, that actually was a band. Forget it. All right, so that's pH 7, neutral. And your blood is pH 7 too, and it pretty much stays that way. When they go to hang an IV on you, they're hanging a solution that is around pH 7 too. If they're not, you should stop them from turning that on. pH 1, this is acid. Now, we've got things like stomach acid. Not that you drink that much, hopefully not. We got stuff down here like lemonade. We'll be playing with that. Various colas might be around a pH 3 or so. As I say, coffee's probably around pH 5, pH 6. Pure water, pH 7. And then we start working our way up. Let's see, a pH of 9. That's about as good as what baking soda can do. pH of 14, in the industry terms, this is known as caustic soda or sodium hydroxide. There's also things like potassium hydroxide, which is a really good drain cleaner. And so we got things like Drano. As a general rule, don't ever eat anything that's got a pH higher than 7 or 8. A, it won't taste good. B, you get too high and it's like a really bad way to kill yourself.
Where does lye fall?
We tend to actually eat on the low scale. I think I heard from Igor, where does lye fall in here? Mm-hmm. Lye is another form of caustic soda. Lye is Drano. Lye's got a pH of 14. Don't eat lye. No, don't do that. So we eat a lot of things down here. This is where sour is. And it's kind of fun. So you can eat stuff that's a pH 1, no problem. Another common ingredient that you probably have had is vinegar, of course. Vinegar has got a pH of 1 or so. Now, that's the pH scale. Now, we'll be talking more about pH as we continue in, but just one of the terms we need to know. Lastly, you know that chemicals are given the 1 or 2 letter code for all of the various elements. And if you were in basic high school chemistry, you had your element chart that you had to memorize, and then always some kid would come in with the elements on their t-shirt and have to go to the bathroom and take their shirt off or something. For this class, happily, for biochemistry, we don't have to memorize all the elements. They're really, in living systems, a handful of elements that are in reasonably high concentration, and these are the elements you need to memorize. They are C is for carbon. I was about to say C is for cookie, but I didn't. C is for carbon. H is, of course, hydrogen. O is oxygen. N is nitrogen. Pretty much those 4 guys, CHON, they make up the bulk of what living things are made up of. Carbon, hydrogen, oxygen, nitrogen, that pretty much covers it. Then we got things like P is phosphorus. We'll see this a bit. Na, which we talked about just a moment ago. This is sodium. The Latin is natrium. K is one of the oddballs again. This is potassium. Potassium, known as kalium in Latin, or by alchemists and things. Then let's see. We might throw in a little bit of calcium, Ca. Iron is Fe, ferrum, but we're not going to talk about that so much. Pretty much, this is the bulk of what you're eating, CHON. There's a whole range of things that are in trace amounts, silicon and nickel and magnesium, but you don't eat them and sit down to a nice big old plate of magnesium. No. So that's what we need to know. So that's the basic chemistry. Depending on how things go down, as I start getting my act together a little bit better here, we will talk a little bit about some organic chemistry, and I'll get some stuff for you probably tomorrow, because there's only so much of this I can actually pull off in one day. Not having you here is not the best. It makes me sad, but we're doing the best we can with it. Yes? Hey, that's all I have to say for now. Thanks for paying attention to my ramblings and stories, and we'll pick back up this week, maybe even a little bit more, because I want to talk a little bit about organic chemistry, which will be the next section, and then that'll set us up for next week. So for now, though, that's all I got to say. I'm out.